Numerical Integration by Jarod, Sava, Joseph, and Jordan. The midpoint rule uses rectangles centered on a point of the line, with part above and part below the line to get a rough approximation of the area under the line. It finds the area of a rectangle that spaces between the boundaries of integration, with the height of the curve's y value halfway between the boundaries. To increase accuracy, multiple rectangles are used, with each rectangle using a separate iteration of the equation. The trapezoidal rule is a more accurate variation of the midpoint rule that uses trapeziums instead of rectangles. Since the trapeziums have a sloped side, they generally give a more accurate estimation than the midpoint rule. The rule uses the boundaries as the two parallel sides of the trapezium, with the height of the interval between the boundaries, and finds the area. Like the midpoint rule, multiple trapeziums are used to increase the accuracy, with either a separate equation for each trapezium or the composite trapezium rule, which can be used. For a linear equation, the trapezoidal rule will give an exact answer. Simpson's rule gives the exact value for a quadratic equation, as this is what it was developed to do. It also gives the most accurate estimation for other difficult to integrate curves, as it uses parabolic curves found from the beginning and a midpoint, then finds the area under this curve. This is more accurate for finding the area under curves, as the rule uses arcs rather than straight lines. Numerical integration can be seen right throughout engineering. A general rule is that if a part moves, calculus applies. An example of how numerical integration is applied in real life would be when measuring the volume of a dam or the area of an irregular shape. For these examples, approximation tools such as the Simpsons or trapezoidal rule are used because it is too hard to measure the exact dimensions and a lot easier to get an approximation. Another example of numerical integration and differentiation in real-life applications is the relationship between displacement, velocity, and acceleration. This relationship can be described both analytically using equations and graphically. Imagine there is a car with acceleration 5 meters per second. Since the acceleration of the car is a constant value and the initial graph has a constant line, we can calculate the exact integration of this graph, which is the area under the line. From this we gain a second graph, which is logically true since the acceleration is the rate of change of velocity. The same applies with the relationship between displacement and velocity. Numerical integration can be used in coal mines and other places where we have large piles of minerals. We can use numerical integration to work out the volume of stockpiles using the height of these deposits. We can use this method since the stockpiles are not in perfect triangles, and in instances we only need an estimate of the total volume, so we are able to use Simpson's rule to find the volume. We can also use the trapezoidal rule for earth filling to find the total earth needed. As we can see from the image, we can split the earth up into trapezoidal sections, and from there we can work out the total area needed using the trapezoidal rule. We use this method because the earth is not a perfect parabola, and we get a much more accurate number of the amount of earth used.